All right, welcome to Roots of Reality. Today I'm joined by Dr. Eliza Kempton, an astronomer whose research focuses on the atmospheres of extrasolar planets. Additionally, Dr. Kempton's research is motivated by questions relating to the diversity of exoplanets that populate our galaxy and how that informs our understanding of our own solar system, as well as planet formation and evolution more broadly. So, Dr. Kempton, thanks for coming on today.
Thank you.
So, just to start off, how did you first get interested in exoplanets and astronomy in general?
Okay, yeah. So let's see. I was always a mathy kid.
Okay.
I got interested in physics in high school, not because I held some long held interest, but because I had a great teacher. And I found that it was something that I liked and I was really good at. I majored in physics in college and I started looking around for research fields that might be of interest to me, and astronomy was exciting. There were a lot of interesting questions that people were trying to answer. And right when I started graduate school, when I started my PhD program, exoplanets as a field, it was still brand new. The
Sure.
astronomers had just found a small number of these planets. It was not a popular field yet, but it was gaining traction. And what I really liked about it was that there were there was just a huge territory of unanswered questions. We really
Sure.
knew almost nothing about these objects. So it was kind of like the Wild West, in a way. There was a lot of growth potential, and studying planets, I don't know, there is kind of a human scale to it, and I enjoy that aspect as well, where you could kind of picture yourself, and we've never been to an exoplanet, maybe we never will, but you can picture yourself going to one of these
Yeah,
places and trying to learn what that place is all about.
for sure. So when you first entered the field, I guess this was kind of the era when the explosion of these kind of super telescopes started to occur, where we could really start to detect exoplanets then and get good details from it.
Yeah, so I mean, initially, when I started graduate school, most of the exoplanets that had been discovered so far, they had we had really only measured their mass. We basically
Okay.
weighed them. Then, kind of right before I started grad school, the transit technique was really coming
Okay.
into into play. And this is the technique where you measure the size of the planet. So this was kind of the first time, if you know the size and the mass of
Yep.
an object, then you can tell basically how dense it is. Is it something really dense and like iron, or is it something big and fluffy, like a marshmallow, or,
Yeah.
or
Yeah.
or like a gas planet?
Right.
So yeah, that was kind of where the state of the field was when I entered grad school. And then some of the like NASA's Kepler mission launched, which ultimately found thousands of planets via the transit technique, and the whole field really just blew
Yeah.
up.
Seems like the past decade or so, exoplanets are being found all the time now.
Mhm.
Um, I think one of the interesting things about this is that obviously, since we our life on a planet, we want to search for things that kind of remind us of ourselves. So like this, quest for super Earths has become kind of a popular topic. Um, can you talk a little bit about like what percentage of exoplanets we've discovered so far are super Earths, and how does one qualify exactly?
Yeah, so when it comes to detecting exoplanets, it's easier to detect bigger objects. In general, it's just going to be a lot easier to
Yeah.
detect something that's bigger than something that's smaller. So, in that sense, at the beginning, we were really only detecting these big gas giant planets. And as our observational techniques improved, we started to find these smaller objects that we initially called them super Earths.
Okay.
Um, a super Earth being something that's bigger than Earth. So initially, we called anything a super Earth that was bigger than Earth, but smaller than Neptune. So basically, smaller than the smallest gas or ice giant in our planet in our solar system, but bigger than the largest rocky terrestrial
Right.
planet in our solar system. So it kind of fills empty gap in planet size in our solar system. We called those super Earths, and we started as soon as our observational capabilities were able to find planets in this regime, these super Earths. We started finding them. So that tells us that that initially tells us, the fact that we just find them right away tells us that they're probably very commonplace. And now today, we know that planets in this size range are potentially the most common type of planet
Okay.
in at least orbiting stars in our galaxy. With again a little bit of a caveat that that this is all colored by what kinds of planets we are actually capable of finding with current technology.
Sure.
So currently, we still are mostly limited to finding planets that orbit fairly close in to their host stars. So certainly, among planets that orbit close to their host stars, these super Earths and another category of planet that we now call sub-Neptunes, which are also smaller than Neptune, but
Okay.
bigger than Earth, are the most commonly occurring type of planet in our galaxy, and probably most stars in our galaxy, or at least approaching half of stars in our galaxy probably have, or sun-like stars have at least one of these planets in orbit. So it's very different from our solar system, where we don't have any super Earths.
Yeah.
Most stars do have super Earths or sub-Neptunes.
Right. And what's like the potential habitability of like a super Earth or whatever? What percentage of them look like, they could potentially have life versus, there's nothing there probably.
Yeah, so we have to kind of back up and say what we mean by could they have life, because we have not
Yeah.
found life on an
Right.
exoplanet yet. We've not found any definitive evidence of life on an exoplanet. So
Yep.
um, the kind of basic way that people in my field think about searching for, well, before even searching for life, right, finding a planet that could be amenable
Yep.
to having life, is this concept of the habitable zone, or sometimes called the Goldilocks zone. So basically, Goldilocks, right? Not too hard, not
Yes.
too
Right.
soft. In
Just
this case,
the
it's
right balance. Yeah.
not too cold, not too warm. And what do we mean? Not too cold, not too warm for what? For liquid water, right? We think that, at least on our Earth, liquid water is critical to supporting any life on Earth. So we want to look for the kinds of planets that could support liquid water, and right. So if you're too warm, if you're too close to your host star, your water is all going to boil off.
Yeah.
And if you're too far from your host star, your water is all going to freeze into ice. So you need to be in that sweet spot. It's still, again, with our measurement capabilities, it's still hard to, because that sweet spot is somewhat away from the host star.
Yep.
It's still somewhat hard to find planets in that zone, but we have found them, and we can tell that that again, it's there's a fairly high likelihood of finding planets in that sweet spot Goldilocks zone, where they might be able to support liquid water. Then we want to actually go and try to find evidence for the liquid water and for life actually being there. That's what
Sure.
that's what we still struggle with.
Sure. Of course. Yeah. That makes sense. So like, what percentage of those planets then could potentially have liquid water on them in terms of the number of super Earths we have been able to identify?
Among the super Earths that we've been able um, to identify, I'm not quite sure of the specific number, but again, it's going to be highly biased by the fact that most of the super Earths that we have found
Yeah.
are on the side where they're too hot, they're too close
Okay.
to their host star. So it's a much smaller fraction of the ones that we found. It's a much smaller fraction that could host liquid water. It's still, if I had to guess, probably a few percent of the ones that we found
Yeah.
are actually, maybe even less, are in that zone where they could host liquid water. But we also know that we're not very sensitive. We're not very capable of finding planets in that zone. So based on the ones that we have found, we know that
Yeah.
there are likely a lot more.
Right. We've found a tiny percentage of the potential planets. Yeah. That makes sense. So, when you're doing this research and you're looking for exoplanets, What do we? I know obviously we're trying to learn about the exoplanets, but at the same time, we probably learn a bit about our own planet through this research. So, what has your research on exoplanets taught you about our own planet?
Yeah. So these objects, I mean, a huge question about these objects is why are they so different from what we see in our solar system?
Yeah,
Right. Before we ever found exoplanets, we only knew one planetary system, right? That's ours. And we had this nice, neat kind of uh, theory about how our solar system formed, which we thought would translate potentially to other solar systems. So
yeah,
if you believe that what happened here was typical, then you'd expect to go out and search for other solar systems, other exoplanets, and find that those systems have similar properties to our solar system.
right.
But instead, what we find is that most of the planetary systems that we find are very, very different. They have a very different architecture. They have different types of planets. They have planets at different distances from their host stars. They don't follow some of the basic patterns that we see in our solar system. So why are the outcomes for all of these planets so different from what we find in our own solar system? And so I've become very interested in kind of the diversity of outcomes, all the different types of planetary systems that nature can provide us with. And one of the big questions that we want to address is exactly why are they so different? What
Yeah,
unfolded differently there than here, and what kinds of information can we glean by not just the fact that the planets are there, but actually observing their atmospheres, trying to measure the gases that are present in their atmospheres, the kinds of clouds and chemicals that are present in those atmospheres. How can that provide us with clues for why what unfolded there is so different from here?
yeah. So, has that then made you kind of think about Earth as being kind of more special compared to what we're seeing around the universe? Since it seems like, it's not as obvious that they have that same type of like perfect situation where life can be forming on a variety of different planets throughout the galaxy. So,
Yeah, so I mean, a huge theme of what we've seen among the exoplanet population is that diversity. So among that diversity, there probably are other systems that have
yeah,
properties that are more similar to our own. But yes, it does make us a little bit more special. And I think, in my case, it's made me, scientists are often skeptical, right? It makes me,
right.
it makes me somewhat skeptical, right? If we do identify a planet that has similar basic properties to the Earth, right? It maybe has a similar mass, a similar size, a similar orbital distance, it orbits a similar star. That diversity of planetary systems that we've seen makes me skeptical that, just because it has these basic properties that are similar to Earth, does that mean it's going to
Yeah,
have an Earth-like atmosphere? Does that mean it's going to have Earth-like oceans and continents? Does that mean it's going to have Earth-like life? I'd say, I'm not so sure. I'd want to learn a lot more
right.
about this planet before I really decide that, this is Earth 2.0 and
Yeah.
we should go visit.
Yeah, that's right. Yeah, going to visit, that's yeah, quite another challenge. Yeah. That's um yeah, it's obviously difficult because you think about obviously how vast the universe is. The potential is obviously seems limitless from where we're at currently in the research. But at the same time, it's not like abundantly clear that these things are just popping up all the time where it's like, oh, this is definitely a candidate for life or whatnot.
Yep. No, exactly. Although I would add that it also opens up the door to the possibility of planets that could host life that is very different from the Earth, or planets that
Yeah.
could have conditions that on the kind of on the exterior seem very different from Earth, but might actually harbor like liquid water,
Sure.
and some form of microbial life. So it means that we have to be a little bit more creative
Right.
about how we think about life.
So we have to, yeah, yeah. I mean, that's a great point. That's something that's actually really interesting to think about because obviously we typically have this very anthropomorphic bias about like how we would envision life taking place. Makes sense, but at the same time, the potential for a diversity of how life develops is a really interesting question to pursue. What do you think are the chances that there is life developing on other planets in a very different way from Earth? I mean, I guess we can kind of have some lens of analysis to look at this from based off of, some of the places we find life on our own planet, which seem like, there's no way a human being could live in that type of climate. But yeah, what do you make of that?
Yeah, I mean, Earth definitely shows us, like you said, these extreme environments on Earth show us that life can thrive in all kinds of environments. We also know from basically a geological record on Earth that life arose very early in the history of our planet, which means it didn't take that long. Once the planet was here,
Sure.
it didn't take that long for life to take hold. So that presents kind of an optimistic view that life could be a very robust phenomenon, and you could find it in lots of places. I would say that 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 kind of a key outstanding question is how easy is it for that initial step of turning from something that's not biology into biology? Is
Sure.
that easy? Is that a kind of universal process that happens either just easily via basic chemistry, or it can happen via a bunch of different possible pathways, so that it's kind of an inevitable outcome? Or did we hit the jackpot here and everything aligned right to get started? And then once you got things started, then life tends to thrive all over the place. I don't know the answer
Yeah.
to that question. I'd like to be an optimist and say that
Yeah.
this happened here and it could happen anywhere else with the right conditions, and life thrives.
Sure. Of course. Yeah. Yeah, it's one of the interesting questions, unfortunately, that we have to kind of wrestle with. In terms of, like, when you look at these exoplanets, are you able to get much insight in terms of how old they might be? And so then being able to calculate, like, okay, if there was life, potentially at what stage could it be in terms of that planet's history?
Yeah, so doing kind of dating the age of
Yeah.
objects in astronomy is kind of it's kind of a weird way that we have to approach it.
Yep.
So it just turns out, right, okay, so the way that we determine the age of a planet, or at least so we estimate the age of a planet,
Right.
is because a planet orbits a star, and we figure the planet and the planetary system and the star were born at the same time. So we look at the star, and we use the astronomical techniques that we use to try to date the age of a star. It turns out that it is fairly straightforward to figure out how old a juvenile star is.
Okay.
But once they hit the so-called main sequence, where they're kind of they're basically in the phase of life that our sun is in, where they're
Yeah.
fusing hydrogen into helium, and they kind of give off like a more or less constant energy output.
Yep.
Then it's harder to tell. And we're talking, right, when we're talking about the age of a star, we're talking in, when they're young, we're talking about tens of millions of years, and then as they get
Right.
into their life, we're talking about billions of years. So it's
Sure.
really hard to tell if a star is a billion years old, or 4 billion years old, or 8 billion
Okay.
years old. Um, Whereas it's actually easier to tell, is it 5 million years old, or 10 million years old, or 40
Okay.
million years old. So it's a long way of saying that we often don't know exactly how old a planetary system is. We can definitely tell if it's very young,
Right.
or if it's more like our planetary system, 5-ish billion years old, a few billion years old. But we don't have we can't tell a lot of gradation kind of in between.
So yeah, a bit of a guessing game, I get, in terms of, yeah, trying to figure out that. Um, would you say that in terms of the plants that we found that potentially could, I guess, hypothetically harbor life, do we know much about their ages? Are they considered to be very old planets that are kind of where you're in that murky territory of the billions, or are they very young?
Yeah, so I mean, most of the ones that we're seriously looking at that we'd want to look at for serious prospects of life would be more in the in the age regime of like our solar system. So
Okay.
they'd be billions of years old. So if life was present, it would have had a long time to evolve. It would be really cool to look at much younger
Yeah.
systems, but they're challenging. They're kind of ornery,
Okay.
like teenagers. Right? The stars tend to be very active. They give off lots of flares and basically when you try to look at the planet orbiting the star, you tend to be kind of swamped out or confused by all of the things that the star is doing.
Yep.
So yeah, we tend to look at these older, more well behaved uh, systems, especially if we're trying to do something very challenging, like look for signatures of like gas signatures of life on a planet.
Yeah, no, that makes sense. Now, when you're doing this research and you're thinking a lot about exoplanets, what's kind of on your mind most? Like, what are you most like looking forward to when you're doing this research? Are you thinking about like, oh, could there be life on a planet out there, or are you just really just thinking mostly about, okay, what's the basic structure of this planet, and just trying to gather those normal details. um, Obviously there's kind of like different aspects to look at this problem from like the sort of sci-fi perspective of that, in this curiosity that we have as being human beings, versus just the more kind of classic analyzing things from the perspective of what do we really know versus projecting our own interests perhaps.
Yeah, so again, I mean, I'd say that this diversity of planetary systems is really intriguing to me. So I like the kind of extreme environments that we can probe with
Hmm.
exoplanets. We have these objects called hot Jupiters, which are gas giant planets that are parked really really close into their host stars, and um, they probably have clouds made up of not like water but of iron, right? Like little iron droplets.
There you go.
So crazy things like that. I have a lot of fun with that. I do have fun thinking about planets kind of from a like geological perspective, like as individual objects. What can we learn about each of these worlds? But I have to say, right now, something that kind of an approach that has gotten me the most exciting is getting back to my training as an astronomer.
Hmm.
You think of kind of classic astronomy, and some people think of classic astronomy as like cataloging things, like cataloging all the stars in the
Sure,
sky,
sure.
cataloging all the galaxies, and so now I can catalog all the planets. Okay, that cataloging is stamp collecting. It's kind of boring, but it's also this amazing opportunity where in our solar system, again, we have this one outcome of planet formation. Things unfolded here in one particular way, and that led to our solar system. And we can study our solar system to death and not actually understand how planets form in general because
Yeah.
we're biased by our system. So going back to the astronomer perspective and cataloging the properties of all the different planets as they vary with, right, like these planets are similar but they all orbit different stars, or these planets are all similar in some ways but they all have different sizes. So looking for kind of population level properties of planets, and how those vary with the kind of star that they're orbit, or the age of the planet, or the size of the planet, and that's a very powerful way to do science. It's like using the population, the full population of planets, kind of as a control experiment. We want to look at this
Yeah.
population of planets versus that population of planets. We want to look at how planets respond to just one change, just one variable, and I
Sure.
think we can learn some really exciting things about how planets form and evolve that, again, we couldn't do if we were just studying our solar system.
Yeah, no, that makes sense. I mean, what is like one discovery you hope happens in your lifetime as an astronomer?
Well, okay. First off, I would really like to see an actual atmosphere on a true super Earth, so
Okay.
on a rocky terrestrial planet.
Okay.
If you're talking about if we want to find life on these planets,
Yeah.
we find liquid water. Well, the first thing we almost definitely need for life is we need an atmosphere.
Okay.
The planet needs to actually have an atmosphere and not just be a rock that's directly exposed
Yeah.
to the space environment, right? That's a very hostile environment. But again, because of the kinds of planets that we are able to study with our current technology, we've had to focus when we observe rocky planets and try to look for like atmospheric signatures. We've had to look at planets that orbit these very small stars called M dwarfs, and
Okay.
these M dwarfs are they're very active, where they give off a lot of flares, they give off a lot of ultraviolet radiation, they give off a lot of X-rays, and so far all of the rocky planets that we've looked at orbiting these M dwarf stars uh, look like they basically don't have atmospheres.
Okay. So they're
Uh,
not very good.
yeah, so like that's full stop to any kind
Yeah.
of searching for life.
Yeah.
So I would love to see, and I mean, I think we can certainly, I think we have a path to get there. I would love to
Right.
see real convincing evidence of an actual atmosphere on a rocky planet. That would be a great start.
So that leads me to my next question then, because I think this is kind of the funny dynamic when you talk to like someone who's actually doing the research versus reporting on exoplanets, because there's a lot of sensationalism, obviously, and media coverage of these things, where I feel like a lot of the coverage of exoplanets, over the past decade or so, seems to be like almost making it feel like it was imminent, that we were going to discover life on some far distant planet or whatever. Um, but obviously, you know there's a lot of conjecture about what these plants may or may not have. And when you talk about convincing evidence, clearly that's not there at the moment. What do you make of how we report on these things? And obviously, to a certain extent, you probably need sensationalism to get people interested in the topic itself. But as someone doing this work on a regular basis, like how do you sort of make sense of how we talk about this topic from a non-expert perspective in the media?
Yeah, so no, I mean, you hit on some really key points there, right? I mean, we want the public to be excited about what we do because what we do is very exciting, and we have seen very interesting, tentative signs of things that, I mean, so right, if you read the scientific paper, it's usually very dry, right?
Yeah,
And
for sure.
it'll have a
Yeah,
lot of this hedging language. We see something that is consistent with the possibility of life, right? So, I think the scientists do tend to be responsible in their
right.
papers about what we have very definitively seen versus what is tentative, requires more follow up, could just be a kind of blip in a measurement, some teeny tiny signal that we're not so sure about. But then the press just, you mentioned the word life, and the press just
Aliens.
loves it, right? It
Aliens
jumps
are
on
coming
it.
right now. That's right.
So yeah, no, it's
Oh
a
my god.
really tricky thing in this field, and we've seen it play out over and over again in the exoplanet field, also in planetary science. Right? I mean, you look at at on various results from Mars.
Yeah.
There was just a paper out last week, and if you look at the paper, it's about rocks on Mars.
Yeah.
The word life is nowhere in the whole,
Yeah.
90% of the beginning
Right.
of the paper, and then there's a tiny little piece at the very end that talks about, this could be consistent with potentially signatures of life, and you look at it in the news and it's just signatures of
Martians.
life on
That's right.
Mars. So it's
Yeah.
it's tough.
That's pretty. Yeah. It's pretty insane. And unfortunately, it just seemed like, obviously the public appetite is for the science fiction view of the world versus the, you know, uh, critical analysis, view of the world. Did you have any type of like sort of humbling experience when you went from being someone who was interested in studying astronomy, to then becoming an astronomer? Like, was there a change in kind of your analysis of the field once you really got into it professionally, in terms of like thinking about, whoa, what's possible versus actually there's a lot more complexity to this than I initially thought?
Oh, sure. Well, first of all, I'll say that I think that if you talk to any academic, being an academic, an academic scientist is just is just choosing a life of humbling experiences
Yeah.
because we're surrounded by people who are, absolutely genius and who are trying to push the absolute envelope
Yeah.
of what we do. But yeah, no, certainly, right. I mean, when I was an undergraduate and I studying physics and doing really well and getting straight A's, I was like, oh well, I can just go out there and solve all of the
That's right.
problems with relativity and quantum mechanics, and I'll be like just
Yeah.
like Einstein. It'll be great. I think and this is a good healthy thing, right? Because
Yeah.
you start your academic road. You go to college, and you should be excited by what you're studying. And then the
Of course.
deeper that you get into what you're studying, you discover how hard it is, and
Also, and reality hits. Yeah.
yeah, why we don't know the things that we don't know. So,
Yeah.
but it's fun.
I think that's, yeah. I mean, whenever you develop an expertise in any field, I think people then start to realize, yeah, just how complex everything is, how much nuance there is to analyzing these topics, which, obviously, if you're not in the field, you don't necessarily realize that. But that's why it's important to have these types of conversations where you can kind of bring to light, what the reality is of doing this work and trying to sort of learn more about the universe. Um, I think that, one thing I've kind of picked up on, I'm curious to hear your thoughts on, is, I think every field at this point in time in the age of social media kind of has like public intellectuals that really, try to promote the work of the field, but also I think there's a tendency to kind of exaggerate, what we know, or kind of, talk about different subjects as if we're on the brink of something that's going to be, completely life changing. Do you think that there's a tendency of certain people, and just the science in general, doesn't have to be astronomy necessarily, but that kind of will speculate much more than I think an academic would want, that's not necessarily that public type figure? Because I think that there's, I think I see a lot over the last several years, there are people that kind of promote these ideas like there's some magic answer to these big questions. And, there's a lot of books that are kind of written. I think one example are like the theories of everything that comes out, all the time. Someone has some new theory of like, oh, this is the universe, this is how it works. I think the same thing probably happens with like, oh, we're going to be finding intelligent life at this time or by this point. What do you make of that?
Yeah, I mean, I think we're kind of lucky in my field in astronomy. I feel like the real big names who are kind of, yeah, this these like public figure scientists,
Hmm.
um, have done a really good job and a responsible job of sharing excitement for. I mean, there's so many amazing things in the universe. You don't have to like really make it
Sure.
up.
Right. Yeah.
So that's been good. I mean, I will say there's a lot of noise out there, especially right,
Yeah.
like you said, in the era of social media.
Yeah.
You can find someone who will say whatever you want.
Yeah.
So that's certainly a challenge. But yeah, I mean, I'm quite happy to see how kind of space positive a lot of people are, and
Sure.
young people too. I have a 13-year-old daughter. I'd
Yeah.
say, over the last few years, like a substantial fraction of her friends think that they want to be astrophysicists when they
Hey,
grow up. And they
there you
don't
go.
just and they don't even just say astronomer, they say
Yeah.
astrophysicist. Like having young girls say, I want to be an astrophysicist when I grow up. I feel like that a positive message has been put out
Definitely.
there,
Yeah.
such that this is something that they think they want. So that's a good thing.
Yeah. No, I mean, I think that's been probably one of the benefits of social media, is that you do have these things perhaps being put into people's kind of minds at an earlier age, and people are thinking about these topics. And obviously, there's been a lot of, public intellectuals that have really helped get people interested in space. Um, I think the side that is kind of more comical is the side where people are like constantly talking about, like, alien life, which is obviously a huge obsession for humanity, and has been in the United States since the UFO obsession in the 1940s. Um, so I guess that's kind of a probably in academia kind of a funny thing to keep track of or to hear about is when while you're doing research trying to understand is there even a chance at all of a certain planet having life, which, as you mentioned, the atmospheres are really not uh, necessarily highlighting that as a clear possibility at the moment for what we have come across. But at the other end of the spectrum, there are people talking about like, oh, there's aliens, like they're gonna be here tomorrow, kind of
Well, they're
ideas.
already here, right?
That's right. Yeah, there you go. That's right. Careful what you say. You might get up going viral with that one. That's right. Yeah, I could easily see that's right, media jumping on that, and all of a sudden, boom, aliens are already here. So problem solved.
Yeah.
I guess that's kind of one of the funny aspects of navigating this because everyone's interested in the topic, but to what level they're willing to be, thinking really critically about what's possible versus what we don't really know, obviously differs from person to person. So par for the course, I guess. So, what are you currently researching then at the moment? Like, what's your current work focused on?
Yeah. Well, so we mentioned the super Earths and the sub Neptunes. I'd say that's
Okay.
where a lot of the excitement for me personally is right now. Again, most commonly occurring kind of exoplanet that we know about. And so I mean, the great thing is the James Webb Space Telescope, right? NASA's James Webb Space Telescope, which launched just a few years ago on Christmas.
Yeah.
Now actually it's flying. It works. It can take beautiful data. We can get observations of the atmospheres of these smaller planets in a really meaningful way that we couldn't before. So it's been an exciting few years getting these kind of transformational observations and trying to make sense of what we're seeing. Um, I'm primarily a theorist, so I calculate computer models of these planets' atmospheres, and we thought we were getting ready for the James Webb Space Telescope for years, and then we actually see the measurements, and they're all a little bit different from what you would expect.
Okay.
So that leads to just this big flurry of activity, trying to or like playing from behind in a way. We have these
Yeah.
measurements, and
Exactly.
now we need to figure out how do we explain them. It's opened up some new questions, some things about just fundamentally like how planets are built. We're rethinking some of that. So it's been a fun time.
Yeah. Well, I mean, it seems like there's a lot of, there's endless amount of research, obviously, in this field. So, and lots of potential interesting findings ahead. So that's really cool. I mean, what's the best way for people to keep track of what you're doing then and following your work?
Oh gosh. Well, I would say read my papers, but I don't think that's the right answer.
That might be difficult for some. I guess for those that are really inclined, yeah,
Yeah,
perhaps.
we try to uh we try to talk to the press. Like you asked about the press, right?
Yeah.
We try to talk to the press regularly whenever we have something that we think is particularly exciting, and we try to explain to them why that's exciting, so that they'll issue a piece that is more focused at the general public. So that's kind of the main way that we've been communicating our science directly to the public. And yeah, we've had some exciting results recently. We have some more coming out.
So I guess in your next press release, you're going to mention then that aliens are already here, and that's the that's I presume that's the next stage of this. Yeah,
Absolutely.
you become the most famous astronomer overnight with that one.
Yeah. But maybe all my colleagues will hate me after
That's right. Yeah, and yeah, there goes your career. That's right.
that. Yeah. I have tenure. Who cares?
Okay, that's right. Well, there you go. Then you could just push that and become. Yeah, I mean, yeah. In today's world, you'll become super famous. That's right. You'll probably be interviewed for like ancient aliens and stuff and all sorts of other things. So
So there are legitimate scientists who've been interviewed on the
I've seen that. Yeah, I mean, I guess it's wherever you wanna make some money and yeah, get publicity. That's have you ever do you ever get invited to go on like different shows or whatnot? It doesn't have to necessarily be Ancient Aliens, obviously, but in general, like, is it pretty normal for different astronomers to get reached out to by different like documentaries or whatever?
Yeah, I mean, it depends on what the reporters are excited about.
Sure.
Yeah, there was a moment when uh, 60 Minutes was reaching out to some people in my field soon after
Okay.
the James Webb Space Telescope was launched, and then they decided they didn't actually decide to report on what on exoplanets. They decided to report on these results from the James Webb Space Telescope about the expanding universe and these very very distant galaxies. So they decided that what we were doing was like
Okay.
not
Not
interesting
exciting
enough.
enough. Yeah. Well,
Probably because
yeah.
we didn't say that we found life,
That's right.
honestly.
Yeah. That's one of
Yeah.
the
So whenever our field has a moment, that's kind of when these bigger news outlets
sure.
start reaching out, or yeah, someone decides to put together a topical show. So it's always it's fun when the opportunities arise.
Yeah, I mean, well, at the same time, like in all seriousness, like it's great though that uh, the field of astronomy and people like you are trying to also like keep things level headed about when we're talking about these things, because I do think that it's one of the big challenges in an era of social media is to make sure people are actually getting realistic ideas about what we're able to do, and not to uh, say that big discoveries are not possible, obviously, but at the same time, when people better understand the process of science and making discoveries in the field of astronomy, for example, it's good to know that people are out there helping people learn that this is complex and it's not just like, oh, big time discovery after big time discovery. And I'm gonna go on some TV show and talk about how aliens are among us right now and yada yada yada. So
Yeah, yeah, no, I mean, right, for your listeners, right? If you see something in the press that says astronomers found life or found signatures of life on another planet, certainly be skeptical first. It's not to
yeah,
say that it's not to say that it's wrong, because hopefully this will happen at some point. But definitely be skeptical first.
yes, that's right. Yeah, typically really really big things take time to unveil, and yeah, it's always good to be level headed and skeptical about it. So, anyway, thank you so much for taking the time to come on the podcast and share all your knowledge and all the work you're doing. And yeah, just really appreciate it. So.
Thank you.